All right, good afternoon, everyone. Let's get started. So today I'm going to start with just a review of where we were last time, just to highlight some of the more important things. So we were talking about this problem of predicting a scalar variable y based on scalar variable x. So y we often refer to as the target or the label. X is usually called the feature. And the data we get to do our machine learning is we get pairs of x, y, and we put an index I on them to index across our data of a total of n different pairs or n samples. And we're starting out simple, and we're using a linear relationship to describe our approximation of how x relates to y. So on one hand, we have this left side where there's an approximate equal to that says the true y is approximately equal to a constant beta 0 plus a scaling term beta 1 times x, or you can think of them as a slope and an intercept term. So this is just an approximate model, and you can see here in this picture that it's not exact. So we have beta 0 plus beta 1x is this red line. The actual examples of x and y are the blue dots, and you can see they're not on that line. So that's why we use the approximation. On the other hand, we do need to make a prediction for every x we're given. We need to come up with a single prediction y, and we're going to call that y hat, and that's going to be exactly equal to our model here. So that's why we have equal on that side, and this is the triangle means it's just a definition. So in this case, there's two things we need to design for our model, these two parameters, beta 0, beta 1. Both are scalars, but we can put them together into a vector, which is boldface, called beta. And we said we're doing this just because linear models are simple, and it's a place to start and get some understanding. Okay, and then the next thing we talked about is how we're going to actually fit these parameters. So we started by saying, let's be a little bit more explicit about the difference between in this case, the training sample yi and the prediction, which we could call yi hat. And we said that the difference, we're going to give that a name, call it epsilon or epsilon I in this case. So that's the residual, and that's taking into account this non-zero error between our data and our prediction. And then we said that what we're going to do is we're going to do a least squares fit, or we're going to minimize the residual sum of squares. So from one perspective, that's like taking all these epsilon i's, summing them, squaring them, summing them together, and that's what we want to minimize. And we can also think about this in terms of the training targets and our predictions, which we're making from the training features. Okay, so this is RSS. This is the thing that we have decided to minimize. And there are other options too. We could have looked at an absolute value here instead of the square. But this is the most common one and the easiest one to work with. Okay, so at the end of the day, we're going to adjust these parameters so that the predictions y hat I are a least squares fit to our training data. And so here we have sort of a recipe that shows up in a lot of problems. We'll see it again in Unit 2. And the next thing we said that sometimes statistics can be very useful. Statistics is just a way of summarizing data to a few simple quantities. And in this case, what we're going to see is that if we create the right statistics, that we can directly solve for the coefficients beta 0 and beta 1. So that's sort of the goal here. So just to start out, we define the sample mean. So if you're given a set of n xi numbers, you just average those numbers, and we call it x bar, and that's the sample mean. For y, our yi's, we can average them to get y bar. Then we have these variances. These are the average squared difference between the samples and their mean. So we have sx squared. It's the variance of the xi data, and sy squared is the variance of the yi data. And we said that sometimes we like to remove the squares and just consider the standard deviations because they have the same units as the data, so they're more easily interpretable. We did a bit of visualization. We saw how these can be easily computed in NumPy. And then we talked about another quantity, the sample covariance, which is sort of similar in spirit to the variance, except it involves two different quantities, in this case, the x and the y quantities, or the x and y data sets. So it's the average of the product of x minus its mean times y minus its mean. And sample covariance tells us how related x and y are in a particular way. And then we said that the sample covariance is itself a little bit inconvenient to deal with because as the size of the x quantities get larger or the size of the y quantities get larger, so does the covariance. So often it's good to normalize this covariance by dividing by the standard deviation of x and the standard deviation of y. And now we get this normalized correlation coefficient, which is always going to be between 1 and -1. And so knowing that coefficient right away, we know something about how correlated x and y are independent of their scaling. So that's convenient. And we had some pictures here of what it means to be positively correlated, negatively correlated, and uncorrelated. But we'll see some more examples today. It's not, the data doesn't always look like this. And the final thing we did, which we'll use today, is we derive these relationships here. Often these sort of quantities show up in an analysis. It's just a simple average of the xi times yi. And we derive that you can write this as the cross covariance of x and y plus the product of those sample means. And then here, this is for the variance. You can write that, this is the average xi squared. You can write that as the variance plus the squared mean. So we'll see how these are useful in a few minutes. All right, and then we had some notation. Any questions on anything we did last time? Okay, great. So we're going to work towards the solution. How do we figure out these betas? So let's first, let me just draw a picture of the scalar case. If you like, you can imagine that what we want to do right now is just select the value of beta 0, maybe forgetting about beta 1. And if you plotted, for any value of beta 1 you chose, if you plotted the RSS as a function of beta 0, you would get some parabolic shape that looks like this. And this is because with a little bit of manipulation, it's easy to convince yourself that RSS is just going to be a quadratic function beta 0. So it has that parabolic shape. So now if I ask you, what is something special that happens at the minimizing location of that quadratic? So visually, we know that it's around here, right? So what happens there that's kind of special, in addition to the function being minimized? So let me ask this to, let's see, is Tyler Sullivan here? Yeah, so what do you think, Tyler?
I'm sorry, can you repeat the question?
What beyond the function being minimized at that point, is there something else that's sort of interesting about what happens at that point to the function? The hint has something to do with the slope. The slope is 0, exactly. So that observation ends up being the key to most of our minimizations throughout this semester. So at the minimizing value of beta naught, the slope of RSS with respect to beta naught is exactly equal to 0. Okay, so that's actually a way to figure out what the minimizing value of beta naught is. if you can come up with some equation for the slope of RSS, and you set that to 0 and solve for beta 0, then you find the minimizing value. So that's how we're doing it. Is that making sense? Okay, so we actually need to do this simultaneously for beta 0 and beta 1 in 2 dimensions, but it's really not much different. So here's the picture in 2 dimensions. It's kind of hard to see, but this is beta 0 here. This is beta 1. This is RSS. And so here again, we have a parabolic shape. It's called, it's a 2-dimensional hyperparabola, but it behaves the same way, essentially. What we notice, it's kind of, the minimum is a little bit hidden here, but at that minimum, whichever direction you look in, if you compute the slope in a particular direction, you will notice that the slope is exactly 0. Or if you just say, what is the slope in the beta 0 direction, that will be 0 at the minimum. And what is the slope at in the beta 1 direction, that will also be 0. So essentially, we just want to set both of those slopes to 0. That will give us a system of 2 equations and 2 unknowns, right? Beta 0 and beta 1. And we're just going to solve that system. So that's how we're going to do it. So in terms of the math, this is how we set up that system of equations. So notice this is a vector because the transpose is a vertically stacked vector. Here we have the partial derivative of RSS with respect to beta 0 on the top, partial derivative with respect to beta 1 on the bottom. We're setting that vector equal to 0 vector, meaning both of them have to individually equal 0. Okay, so that is essentially how we're doing it. So there are a few details here. You might say, well, does this always work? And no, it doesn't always work. It actually does work always in this case of RSS because it's quadratic. We're going to get into some of those details a little bit later in the course. Right now, I don't want to dive too deep. But yes, this definitely does work with RSS. And it works in part because it works as long as what's called the Hessian is positive semi-definite. So again, we'll get into this, but for now, you can just trust me that it works. Here's another picture of sort of the same thing. So if you look on the bottom here, we have a contour plot, and here's another contour plot. So the contours are like if you look at a topographic map, maybe you've seen that before, along each one of these contours are the set of beta 1, beta 0 pairs that all give the same value of RSS. So RSS is the same around that. They turn out to be ellipses in this case. RSS is equal at all those points on that ellipse and so on. So we'll often look at these contour plots. This plot on the bottom actually shows using arrows the value of the gradient. So this vector here is called the gradient. This is a vector of partial derivatives. And in this bottom plot, those little arrows show you the direction of that vector, and they show the magnitude of the vector according to the length of the arrow. So the longer the arrow, the longer the gradient, or the steeper the surface. And so what do you notice right here in the center? Let's see, is Nityasri Suresh here? Yes, so what's happening there to the gradient at the center, according to the arrows?
It's diminishing.
Okay, what happens exactly at the minimum? What's the value of the gradient? 0, exactly, right? That's consistent with what the arrows are showing to us. Okay. Good. So what we're going to do on the next page is we're going to derive these expressions, but I'm just going to write them down first to sort of show you a target of where we're going. So it turns out that for beta 1, we can get the optimum value by this ratio SXY over SXX. In other words, that covariance divided by the variance. Or we can write it in terms of rho xy, which is that correlation coefficient of sy on the top and sx on the bottom. Okay. In terms of beta 0, that ends up being y bar minus beta 1 x bar. So we're going to derive these on the next page, or next couple pages, but for now the point is that these optimal parameters, the ones that give you the best possible prediction in terms of minimizing RSS, are completely described by these 5 statistics that we talked about. Mean of x, mean of y, standard deviation of x, standard deviation of y, and this this correlation coefficient. Or alternately, these two and these two. So with just a few statistics, we know everything we need to know about our data to come up with the optimum linear regressor or predictor. Okay. All right, so any questions so far? Okay. All right, so let's do this derivation then. And the things we're doing here are things that we will be doing all semester. So very common kind of operations like taking gradients, applying the chain rule, and so on. So again, our goal is to set these partial derivatives simultaneously to 0. So this is going to give us a set of equations, 2 equations and 2 unknowns. So let's first tackle the first one. So we have that we want to take the partial derivative of beta 0 with respect to RSS, and I'm going to write RSS in terms of the sum over I, and we have yi minus beta 0 minus beta 1 times xi, that whole quantity squared. Okay, so let's take a look at this. So our task is to do this differentiation. So there's a few things, key things to remember, which we'll see over and over again. First of all, differentiation is linear, which means that it can pass through that summation. So the derivative of this sum of quantities is the sum of the derivatives of each one of these guys here. So just in your mind now, just imagine that this thing is here, if you like. Now, we're just taking the derivative of this scalar quantity here. So, how do you think we should proceed? So is Robert Voris here? Yeah. What do you think? How do we proceed with this?
Apply the derivative to each of the coefficient, essentially.
Well, so what about this here?
Don't take the derivative of the square.
Okay. So there's a name for this procedure. Do you remember it?
Nope.
Chain rule.
Not changing.
Chain rule. So we have kind of a concatenation of functions. We have like the square being applied to a whole bunch of other stuff that we need to deal with. So that's called the chain rule when you kind of use those all together. So with the chain rule, it basically says it's going to be 2 times this thing in parentheses times the derivative of the thing in parentheses. So let's put a 2 out here. And I'll move the 2 in front of the summation, but the sum is there too. So 2 times the thing in parentheses, so I'll write that, yi minus beta 0 minus beta 1 xi. And now we have to take the derivative of the thing in parentheses. So what is the derivative of that with respect to beta 0? And I'll ask this question to, is Dhruv Weaver here?
Yeah.
Yeah.
Sorry, I was writing that down. Could you repeat that?
Oh, sorry. What's the derivative of the thing inside the square, the parentheses with respect to beta 0?
I believe it's partial derivative of yi over partial derivative of beta 0.
So it's just this, we're
Minus-
taking the derivative of this with respect to beta 0. So it's super simple. Maybe you're overthinking it.
I probably is it just yi minus?
So if this is a constant that doesn't depend on beta 0,
It stays, right?
no,
Oh,
it's
it becomes
0.
part- Yeah, yeah, yeah.
It's 0.
So
there's-
brush up on that.
Only one term, yeah, brush up on your calculus if needed, but this is the only term that matters to us. So what's the derivative of this?
That's gonna be 1, right?
Minus 1
Minus one, yeah, yeah.
because of the negative. Okay, so I'm going to put that minus out front. So basically that's it. That is the expression we want. Okay. Let's repeat this again. For the next line, it will be pretty similar, but just slightly different. So we start out the same. We have this quadratic. Now we're differentiating with respect to beta 1. We again apply the chain rule. So we're going to again have that sum. We're going to have a 2 as before because it's going to be 2 times the thing in parentheses times the derivative of the thing in parentheses with respect to beta 1. So let me write the thing in parentheses. It's the same as before. Okay, and then finally we have to do the derivative of the thing in parentheses with respect to beta 1. And is Ting-Jun Wu here?
Yes.
Yes. So what do you think that last thing we need to add is? Minus xi, exactly. So we'll put the minus in front, but the xi needs to be inside the sum, right? I can't move that out front. So that's it. So that's the first step at least. So now we just need to rearrange things and write them in terms of those statistics, and everything will simplify a lot. So I think the easiest way to proceed is to try to turn these expressions into something that looks more familiar. So we're not used to seeing the negative and the 2 in front of those sums. So let's multiply both sides of both expressions above by minus 1 over 2n. That will cancel out the minus. It will replace the 2 with a 1 over n. And we're doing it to both sides. So if I multiply 0 by that, that stays the same. And on this side, I'm just going to basically exchange this with a 1 over n. Right? So that's something we can do. So if we look at the first case, this, I'm just writing that down here. Okay, so this is essentially where we're starting. Okay, now this might look more familiar because we have these averaging sums and we have some stuff in here. So now, next step, we can just expand this sum into 3 different sums. So we have the average of the yi's, which is here. We have the average of these minus beta zeros, which is just minus beta 0. And we have the average of these terms, which is minus beta 1 times the average of the xi's. And immediately we see that this is y bar, right? The mean of y. This is x bar. And so this is where we get that simple expression we saw on the previous page. Beta 0 is y bar minus beta 1 x bar. So all I did there is I basically took beta 0, minus beta 0, and I moved that to the other side. And then I got beta 0 equals y bar minus beta 1 x bar. Okay, is everybody good with this? Okay, and so that was actually one of the 2 equations. So we now just need to work on the other one. So I know what beta 0 is in terms of beta 1, but we still need to figure out what beta 1 is. Okay, so we're going to do the same thing with the second equation. Multiply both sides of this by minus 1 over 2n, and that will give us this. So here, notice we have the xi, whereas before we did not. So that's the difference. But we proceed in the same way. We just expand this sum into 3 terms. Okay, so like for the middle term, I can move the beta 0 out front, and then all I have left after that is the average of xi, which is x bar. And then for the last one, we can move the beta 1 out to the front, and then again, we get an average, but now it's an average of xi squared. Okay. And there is where we have an opportunity to use some of those equations we derived earlier. Okay. So is everybody good so far? Ready to move on? Okay. So let's plug. So in this equation, we have this beta 0 term, but we actually have an expression for beta 0 in terms of beta 1. So let's plug that in. Plug this into here. And as a result, we will have something in terms of beta 1 and then something else in terms of beta 1, and now we can solve for beta 1. Okay, so first thing we get is this beta 0 gives us a y bar. So that gives us this over here, those terms. And then what remains is we'll have this beta 1 term, but then we're also going to have a beta 1 times x bar times another x bar, or x bar squared. So I group things together in the hope that these might look familiar. So what do you think? So is Zhenyu Yang here? So what do you think the first expression is? This one. Yeah, what do we call that? Remember the symbol? S. Yes, right, SXY. Okay. And what about the next one? Is Juchen Yang here? Yeah. So what's the second expression there? This one.
Called it SX.
So this is the variance, right? So this is the variance, and then this is the covariance. Okay, and then we're essentially almost done. We just bring this term to the other side, and then we divide both sides of the equation by SXX, and we get this expression we had here. So that's going to be beta 1 is SXY divided by SXX. Okay, so everybody good with that so far? Okay, so there's something else we can derive too, which is the minimum value of the RSS. So we know how to minimize it, but we might want to know what is the actual minimum value we get. So to do that, we can start with the RSS expression and plug in our beta 0 expression from here. And that will give us the beta 0 will turn into this y bar and beta 1 x bar. Now we have a quadratic. We can expand this into the first term squared, the cross terms here, and the second term squared. And of course, each one has the sum over I. Okay. So once again, maybe some of these terms look familiar. Let's start with the first one. Bowen Zheng? Yes, what do you think that first term is? What is this one? Okay, we can, let's see, try, is Abhishek Apana here? Abhishek? No. Okay, what about Saraswati Arunachalam? Yeah, so what's that first expression here?
Variance is y1.
Exactly, but there's a little trick.
N is y1.
We need an n, right?
1 by n.
Actually, n times,
Oh.
right? because it's missing the one by n. Yeah. Okay. And yeah, so the other ones I think you can recognize are similar. The next one is n sxy, and the final one is n sxx. Okay, so, and if we do one more thing, which is plug in this expression for b, or beta 1 here and here, you can see we have, okay, this is the first term here. The second term, we're going to have minus 2 times this times this. So we get sxy squared in the numerator and sxx in the denominator. The last term, we have this guy squared times this. So that will give us this. Now we see that actually these two terms here are the same. It's just the first one is scaled by minus 2. So together they give us this. And to make things a little cleaner, we can pull out the SYY, bring it to the outside. First term is a 1. Second term is this, which might look kind of familiar. Let's see if is Ethan Garrett here? Yeah. So Ethan, what do you think? You have a guess of what that last expression there is? How can we simplify the thing in parentheses, basically? Just focus on that.
Imagine the sample correlation coefficient.
It is definitely related to rho xy. Is it just rho xy, or is it some modification of it?
Take out a
So if you remember, rho xy is sxy over sx times sy. So how is this one different? And there's one other little trick. You have to remember, how does sxx relate to sx? Okay, so sxx is the variance, is another way for writing variance, and variance is just the squared standard deviation. So this is just the square of that. So do you see it now? These terms are the squares of those. This term is the square of that. So yeah, altogether we just have the square there. This is the squared correlation coefficient. Okay, so that concludes the derivation of RSS. At least this is the RSS, the minimum possible RSS, or the RSS at this least squares estimate. It's the smallest it's possible to make it. You cannot make it any smaller. It's impossible. So, all right. Any questions? All right. So we're not done talking about this, but that ends this derivation. So let's step back and come back to our demo and visualize what we have. So if you remember, this is our data set, miles per gallon as a function of horsepower. And even though it's not really perfectly linear, we're still applying our linear model to it, doing the best we can. And in particular, we're trying to minimize the sum squared of all those errors. And when we do so, we now derived exactly how to do so. So this is how you can do it in Python. You compute the means of x and y, the variances of x and y, the covariance of x and y, and you can see I'm just doing that all with the mean command, pretty simple. So I guess I should point out something that's maybe, if you're not used to working with NumPy. So remember, x is a vector. It's like a column vector of all our samples. Or actually, in NumPy, NumPy does not, unlike MATLAB, NumPy does not have any concept of row versus column vector. In MATLAB, everything is a matrix. So a vector is like a matrix that either has one column or one row, however you set it up. But in NumPy, a vector is just kind of a list of numbers. It doesn't really have an orientation. Okay, but that's how it is. So NumPy is smart enough here that if you take this vector and you subtract a scalar, it does what you would expect. It subtracts that scalar from every entry. Okay? And now you get a new vector. And now if you take the square of that vector, again, that's something that you wouldn't want to write down like on a homework and an exam, a vector squared. I would take off points if you did that. But in NumPy, you can do this kind of shortcut where it knows that what you probably meant is that every element is what you want to square. And so that's what it does. So this is an instance of what's called NumPy broadcasting. Broadcasting. So these like simple operations, it knows how to broadcast them across vectors, across matrices. It does smart things whenever they're well-defined. Okay, so here we will again have another vector, and then we're taking the mean of it. So everything works out fine. Here's another instance of something that is kind of weird. You wouldn't want to write this down on a test, but this is a vector times a vector. So NumPy is smart enough to mean, okay, you can't multiply a vector times a vector. What you can do is you can multiply them element-wise. And so in NumPy, this single asterisk represents an element-wise multiply. This is very different than in MATLAB. In MATLAB, a single asterisk is a matrix multiply. And if you want to get an element-wise multiply in MATLAB, you have to do dot star. Python, it's kind of reversed. Star by default is element-wise, and if you want to do a matrix multiply, you got to do something a little different. It's not a dot star, but there's a couple other options. We'll get into them. After that, everything else are scalars. We have not yet talked about r squared, but we'll talk about that very soon. But anyway, here are the coefficients you get from doing this, and here we're plotting the regression line, which is basically like our y hat versus x, and you can see it's doing, as best as possible, you could possibly fit linearly that data set. Can't do any better than that in terms of minimizing RSS. Okay. All right. Any questions? Okay. There's some nice documentation in NumPy itself on NumPy broadcasting. I believe I have links to it on the main GitHub page. But it describes in gory detail all the stuff that it does for broadcasting. Okay, so let's continue, and let's get back to this notion that we briefly talked about last time, which is how do you know, like you're given a data set, you know it's not perfectly linear, can't be perfectly linearly fit. So you apply, or you're wondering, should I apply a linear fit to this data set? Is it any good or is it just plain bad? So we're going to come up now with a quantifiable metric that tells us how good or how bad is a linear fit on a given data set. So we're going to do this. This is sort of the standard way people look at this. And the way that I like to tell the story, it's really just a normalized version of RSS. So let's first of all think about RSS on its own. Come back to the definition of RSS. There's a couple issues with RSS on its own. Where do we have it? Okay. So as you can see, one issue with RSS, when you use it on its own, is that the bigger your data set, the bigger n is, the more terms in the sum. And so RSS just keeps growing and growing and growing, right? So if someone says your RSS is 1,000 and you say, wow, that sounds like a big number. Well, if you have 1 million samples, it's actually a really small number, relatively speaking. It's because you have so many samples, that's why it's big. So that's one thing that's not ideal about RSS, is that it grows with the number of samples. So it makes sense then to normalize it by the number of samples n. And now it's going to be independent of sample size. So that's the first thing we're going to do. The second thing we're going to do is notice that even if you normalize by sample size, RSS grows by the size of the targets, right? So if I double my targets y, then RSS, what will happen to it? Will it double? The square. It's the square, right? Because so it will quadruple, right? So that's the other issue, is you don't want necessarily to have that dependence of the target size in RSS. So that's the second normalization we're going to do.
What's a target?
Target is y.
Uh,
Yeah. So there's kind of two names I use for y: the targets or the labels. So the larger y is, like, if y are like in the size of tens or hundreds or thousands, RSS will grow significantly. So that's what we want to control. So first we said let's consider RSS divided by n. That gets some improvement, but it's not everything. Let's also consider dividing that by the variance of y. So now we have something that as y grows, both the RSS and the variance grow at the same rate, so you have removed that scaling as well. So now you have a quantity which is actually very useful, where you can just look at that value and get a lot out of it. Now it turns out that the quantity that's most often reported is not exactly that, it's 1 minus that. 1 minus RSS divided by n, that thing, divided by RSY squared. And this thing is given the name R squared through all of the statistical literature and machine learning literature. So R squared, it's called the coefficient of determination. And there's sort of a longer story to why it has that name. It's a bit more complicated. You're welcome to read up on it on your own. It's given in the Wikipedia link here. But I'm not going to get into that definition and exactly what's meant by that. But I do want you guys to understand, roughly speaking, what it means when you get an RSS of a particular value. So what's the largest RSS, what's the largest R squared we can get? Let's think about that in terms of what's the smallest RSS we can get. So let's see, is Rava, Teja, Bijan, and Polly here? Yes, what's the smallest RSS we can get? No, the best RSS, the smallest. Just think about RSS as a quantity, something we want to minimize, right? What's the absolute smallest we can get? 0, exactly. So now you can see that this thing gets smaller. It's negative RSS. So the largest that R squared can be is 1, right? So that's the absolute max. You can never get an R squared larger than 1. It's just simply impossible. So that would be R squared equal means the predictor is perfect. It means your data lies on a line. Okay, what about the opposite extreme? It's not quite as easy to talk about, but let's consider what I will call a trivial predictor. This is the best predictor you can make without looking at any of your features, ignoring your X data altogether. The most sensible thing to do is for every yi, just pretend it's the mean of the yi's. Right? So I'm completely not even doing any prediction. I'm just coming up with like a sensible value for yi, just the mean, y bar. And if you do that, it turns out you get R squared equals 0. So that's sort of like the opposite extreme. Let's think about it from another okay. So I'll explain it from another way, from another perspective in just a moment. So under normal circumstances, your R squared is going to be between 0 and 1. It should never be larger than 1. We said it's impossible. And it should not be smaller than 0. However, it can be. Because, you can do something crazily bad, right? And you can get an arbitrarily small negative R squared. So that's certainly possible. Just, choose y hat randomly and as large as you want. The larger and larger you make it, the larger RSS gets, the smaller negative R squared gets. Okay, but let's also think about the optimum RSS. So we derived that. We derived this expression. This is for a given data set. This is the smallest RSS can get. And we saw that this depends on rho xy and sy. But now let's figure out what that means about r squared. So if we have this RSS, we're going to divide by n, divided by sy squared. That means we're going to divide by these. And then we're going to take 1 minus that. That gets rid of the 1 minus. At the end of the day, we get that r squared equals rho xy squared. Okay, so this is for the RSS minimizing values. This is what our r squared can be. So what's the worst case, the smallest r squared when we use the least squares values? So let's see, is Demi Huang here? Yeah. What's the smallest that version of r squared can get? How small can this get? Can it go negative? No, right? It's a squared quantity, so it can't go negative. But it can be 0, right? We saw examples of data sets, saw those little pictures where we had the rho xy equals 0. So this quantity, the smallest is 0, and that's sort of like this other lower bound. So whenever you use the RSS minimizing values of beta, your r squared is always between 0 and 1. Whenever you do something not so smart and you don't do the RSS minimizing, that is when it's possible to get r squared negative. But if you make a good design, it will always be between 0 and 1. Okay. Great. So okay, so here's some pictures then. So just to summarize, if rho squared is approximately equal to 1, then the least squares linear model gives it a good fit. If it's approximately equal to 0, it's a bad fit. And yeah, if it's in between, if it's like 0.5, then, well, that's what it is. It's hard to really say whether it's good or bad, but you just know it's not close to 1, it's not close to 0, it's somewhere in between. So now that we realize that this rho xy really tells us all about how good a linear fit will be. And so we saw this picture before. This was different examples of rho xy. And one point I wanted to make here is that these all have the same rho xy. So in this case, the data is fitting perfectly on a line. The lines have different slopes. It doesn't matter. What does matter is that the slope is positive. In that case, this rho xy will always be 1. The other hand over here, these all have negative slopes, so rho xy in all these cases will be minus 1. Right? What about this middle case? It's kind of a weird case. Where do you think rho xy will be there? Let's see, is Lahari Kari here? Yeah. What do you think rho xy will be? So let me try to help you by remembering what the so in this case, what is SY? What is the standard deviation in the vertical dimension? 0, right? Okay, so we have 0 here. So is it infinity or no? What about this? This is also 0. So that means we have 0 divided by 0. So it's undefined. So that's why there's nothing written here. Okay. So yeah, in that case, but that's a really weird thing to happen. If you got a data set like this, that would mean that all of your yi's are exactly the same value. So hopefully you would see that, you'd know like, I can't do prediction here. This is garbage. Not even going to try. Okay. Another interesting thing are these pictures. So these are all examples of data sets that also have row xy equals 0. So we previously saw this one, but that's not the only way it can happen. What's interesting about these, I mean, as a human, you look at them and you see clear structure in all those cases. But the structure there is not a structure that shows up as correlation, right? And from another perspective, in some of these cases, you could make a decent prediction in principle. Like here, you could make a predictor like this. It wouldn't be perfect, but it'd be pretty good, right? But does that bother you or not? So in this case, we said the optimal linear predictor, this RSS minimizing thing, would have an R squared of 0. Be terrible because this row xy is 0. So does it make sense that there exists this other thing that does pretty well? Any questions? Why does it make sense? What's the difference between this and the linear? Anybody have a guess? It's nonlinear. Exactly. So when you restrict yourself to these linear predictors, yes, they all fail completely on these data sets. But if you allow something more sophisticated, then you can exploit other forms of structure in the data. Okay. But it's just not, linear methods can't exploit these forms of structure. Okay, good. So the very last thing to talk about, just one more slide in this unit, is that does not mean that linear methods are useless. So here we have, this is the data we're working on. We said that this data doesn't have a great linear fit, but we hypothesized just by looking at it, maybe we could fit it with some sort of inverse model. So you might say, oh, that sounds terrible. Do I then have to go and do this big derivation that we did, earlier today, to derive this whole new class of estimators for inverse models? And the answer is no, not really. You have the option of pre-processing your data. So you take these targets, mile per gallon, and instead you just invert them, and now you have a new data set. You can call them ZI if you want. And now when you plot that new data set, which is 1 over miles per gallon, you get something that looks very linear. So now you take all the methods we discussed so far. We have the equations and everything. You compute the statistics, you compute beta 0, beta 1, you make the predictions. You'll get predictions in terms of z hats, and now you invert those to get back to mile per gallon. And the equivalent, or the effective estimator you get by doing that is this green line. Okay, so by doing this data pre-processing and post-processing with linear in the middle, you can do a lot of sophisticated stuff. It's not exactly the same as designing the optimum nonlinear estimator. It is different, but it's a decent approximation, and it's easy. That's the point. So on the homework, so there's a homework assignment posted. I posted it last Friday. It's due this Friday at 4 p.m. You'll have one problem at the end, where I give you some sort of nonlinear data model, and you have to figure out, it's not an inverse, it's something a little different. You have to figure out, how am I going to make it linear? And there's another problem, which is just a small variation on some of the derivations we did here, where I said, what if you know that the beta 0 parameter equals 0, and so now you have to derive the optimal beta 1. So the intention is to kind of go through this again and figure out from first principles the expressions for the optimal beta 1 alone. Okay. And other than that, I think the other problems are pretty easy, but that's the homework 1 that's due. And then I was hoping to start unit 2 today, but I guess probably a good time to stop. Class is almost over. So that's it. If any of you guys have, I have one more question for all of you. So there was this issue with the quiz 0 with it showing up as muted. Is that solved, or is it still muted?
I'm the link edit.
Okay. It's still muted?
Still
Or
muted
For everyone else, is it muted? Because I saw a number of people took it multiple times. So for those people that took it multiple times, do you know your scores per time? Okay, so, all right, so it's not muted. So maybe we can figure out what's going on with you.
I can show you on.
Okay, but I think it's working now. So, but if anyone has trouble with that, let me know. And all right, see you guys on Wednesday.